Depleted uranium is uranium with a lower content of the fissile isotope U-235 than natural uranium. Uses of DE take advantage of its very high density of 19.1 grams per cc. Civilian uses include counterweights in aircraft, radiation shielding in medical radiation therapy and industrial radiography equipment, and containers for transporting radioactive materials. Military uses include armor plating and armor-piercing projectiles. Most depleted uranium arises as a byproduct of the production of enriched uranium for use as fuel in nuclear reactors and in the manufacture of nuclear weapons. Enrichment processes generate uranium with a higher than natural concentration of lower mass number uranium isotopes, with the bulk of the feed ending up as depleted uranium, in some cases with mass fractions of U-235 and U-234 less than a third of those in natural uranium. Since U-238 has a much longer half-life than the lighter isotopes, DU emits less alpha radiation than natural uranium. DU from nuclear reprocessing has different isotopic ratios from enrichment byproduct DU, from which it can be distinguished by the presence of U-236. DU used in U.S. munitions has 60% of the radioactivity of natural uranium. Trace transuranics have been reported to be present in some U.S. tank armor. The use of DU in munitions is controversial because of concerns about potential long-term health effects. Normal functioning of the kidney, brain, liver, heart, and numerous other systems can be affected by exposure to uranium, a toxic metal. It is only weakly radioactive because of its long radioactive half-life. The biological half-life for uranium is about 15 days. The aerosol or spallation frangible powder produced by impact and combustion of depleted uranium munitions can potentially contaminate wide areas around the impact sites, leading to possible inhalation by human beings. The actual level of acute and chronic toxicity of DU is also controversial. Several studies using cultured cells and laboratory rodents suggest the possibility of leukemogenic, genetic, reproductive, and neurological effects from chronic exposure. A 2005 epidemiology review concluded, in aggregate, the human epidemiological evidence is consistent with increased risk of birth defects in offspring of persons exposed to DU. History. Enriched uranium was first manufactured in the early 1940s when the United States and Britain began their nuclear weapons programs. Later in the decade, France and the Soviet Union began their nuclear weapons and nuclear power programs. Depleted uranium was originally stored as an unusable waste product in the hope that improved enrichment processes could extract additional quantities of the fissionable U-235 isotope. This re-enrichment recovery of the residual uranium-235 is now in practice in some parts of the world, e.g., in 1996 over 6,000 metric tons were upgraded in a Russian plant. It is possible to design civilian power-generating reactors using unenriched fuel, but only about 10% of those ever built utilize that technology. Thus most civilian reactors as well as all naval reactors and nuclear weapons production require fuel containing concentrated U-235 and generate depleted uranium. In the 1970s, the Pentagon reported that the Soviet military had developed armor plating for Warsaw Pact tanks that NATO ammunition could not penetrate. The Pentagon began searching for material to make denser armor-piercing projectiles. After testing various metals, ordnance researchers settled on depleted uranium. The US and NATO militaries used DU penetrator rounds in the 1991 Gulf War, the Bosnia War, bombing of Serbia, and the 2003 invasion of Iraq. It is estimated that between 315 and 350 tons of DU were used in the 1991 Gulf War. While clearing a decades-old Hawaii firing range in 2005, workers found depleted uranium fins dating from the 1960s and 1970s that were from training rounds from the formerly classified Davy Crockett recoilless gun tactical battlefield nuclear delivery system. These training rounds had been forgotten because they were used in a highly classified program and had been fired before DU had become of widespread interest. More than 20 years before the Gulf War, production and availability natural uranium metal contains about 0.71% U-235, 99.28% U-238, and about 0.0054% U-234. The production of enriched uranium using isotope separation creates depleted uranium containing only 0.2% to 0.4% U-235. Because natural uranium begins with such a low percentage of U-235, enrichment produces large quantities of depleted uranium. For example, producing 1 kilogram of 5% enriched uranium requires 11.8 kilograms of natural uranium, and leaves about 10.8 kilograms of depleted uranium having only 0.3% U-235. The Nuclear Regulatory Commission defines depleted uranium as uranium with a percentage of the 235U isotope that is less than 0.711% by weight. The military specifications designate that the DU used by the U.S. Department of Defense contain less than 0.3% 235U. In actuality, DOD uses only DU that contains approximately 0.2% 235U. Depleted uranium is further produced by recycling spent nuclear fuel, in which case, it contains traces of neptunium and plutonium and has therefore been called dirty DU, although the quantities are so small that they are considered to be not of serious radiological significance by ECRR. Uranium hexafluoride. Some depleted uranium is stored as uranium hexafluoride, a crystalline solid, UF6. In steel cylinders in open-air storage yards close to enrichment plants. Each cylinder holds up to 12.7 tons of UF6. In the U.S., 560,000 tons of depleted UF6 had accumulated by 1993. In 2008, 686,500 tons in 57,122 storage cylinders were located near Portsmouth, Ohio, Oak Ridge, Tennessee, and Paducah, Kentucky. The storage of DUF6 presents environmental, health, and safety risks because of its chemical instability. When UF6 is exposed to water vapor in the air, it reacts with the moisture to produce UO2F2, a solid, and HF, a gas, both of which are highly soluble and toxic. The uranyl fluoride solid acts to plug the leak, limiting further escape of depleted UF6. Release of the hydrogen fluoride gas to the atmosphere is also slowed by the plug formation. Storage cylinders are regularly inspected for signs of corrosion and leaks, and are repainted and repaired as necessary. A tenfold jump in uranium prices has transformed approximately one-third of the U.S. depleted uranium inventory into an asset worth $7.6 billion, assuming DOE re-enriches it. There have been several accidents involving uranium hexafluoride in the United States, including one in which 32 workers were exposed to a cloud of UF6 and its reaction products. One person died, while a few workers with higher exposure experienced short-term kidney damage. None of them showed lasting damage from the exposure to uranium. The U.S. government has been converting depleted UF6 to solid uranium oxides for use or disposal. Such disposal of the entire DUF6 inventory could cost anywhere from $15 million to $450 million.